Okay, so my presentation is entitled Coarse Contrastive Recommendation Algorithm based on Hypergraph Convolution. The recommendation systems are one of the most successful applications in the fields of data mining and machine learning. They provide users with personalized platform services that meet their needs. They also can be useful for enterprises by increasing their revenue. However, the performance of most recommendation systems is far from ideal. This is connected with several problems such as high cost of data collection and complex information about the interaction of users and items, and also the sparse data of effective user-item interaction. Despite quite good results exhibited recently by the recommendation systems, there are several problems with the recommendation system. The most important are listed here. The first is the problem that recommendation systems rely on users to generate their own data, which makes it difficult to obtain effective labeling information. And the second problem is that graph convolutional network-based recommendation models are susceptible to the noise of user-item interactions. To cope with these problems, we propose our own model, which consists of three main modules. The first module here is a hypergraph convolutional model. In this model, we adopt graph augmentation to obtain new views of user-item interactions. After that, for two views, we construct a user hypergraph set and the item hypergraph sets for online view and for and use this module to produce hypergraph set and item hypergraph set for target view based on interaction information obtained from data sets about interactions between users and items. Then, similar to the known methods, the characterization of users and items is carried out using the convolutional operation. The second model is a momentum-driven twin network-based model. Both online and target networks, use the gated dual hypergraph-based convolutional model as the network structure. We use the momentum update mechanism to optimize the target network's representation learning model during the parameter training. This aims at utilizing the characteristics of momentum update mechanism to encode historical information in the target network, and thus we can guide online network to learn to explore richer and more effective feature representation. At the same time, the symmetry of comparison network is enhanced by this parameter updating method to alleviate the possible training collapse problem. Negative sampling training strategy based on coarse learning is used to solve the problem of too much randomness of negative sampling in contrast learning. We introduced the method of coarse learning. In the negative sampling process, first we introduce the scoring function here to sort the negative samples from easy to hard. And in addition, we use also the pacing function, which is used to control the negative samples into the training process. Then the mutual and consistency information between two views is maximized. Then we train the system, the model, and finally we can use the trained model for making predictions. Dual hypergraph convolution model mainly uses two chi sub-hypergraphs in online and target views to obtain the potential features of users and items behind different interaction types. It is obtained by aggregating and propagating the future representation of users and items through the hyper-edge aggregation and propagation of corresponding hypergraphs, which were constructed on the basis of different interaction types in two hypergraphs through convolution operation. To study the efficiency of the proposed model, we use two real-world data sets from Amazon and Alibaba, and statistical parameters of these data sets are given in this slide. To comprehensively test the performance of the proposed model, we study the following. We carry out the following experiments in this paper. The first is comparison of performance using the chosen metrics with the known methods. Second experiment is ablation analysis, in which we study the contribution of each component of the proposed model to its performance. And the third is hyperparameter sensitivity analysis, in which we study the effect of the hyperparameter on the performance of the model. The first experimental result, the results of the first experiment are given here. We can see the comparison of 8 methods using 4 chosen metrics. The 4 metrics were checked for both data sets, and we see that the simplest methods, which are based on simple homogeneous graphs, performs poorly, probably because they do not deal well with non-planar relationships between the nodes. Better parameters are showed by these 3 methods, but this dual HGCN works best among them because it can better capture the interaction information between different interaction types by designing the information transfer mechanism between hypergraphs. But the best performance is shown by the proposed model for both data sets. So this experiment confirms that the proposed model is effective. Then we run the ablation test to check the influence of components of the model on its performance. And here we see the table with comparison. Init is the only feature in its initialization model only. And we see also 4 chosen metrics and comparison for 2 different data sets. And we see that in this case, the performance is not very good. When we introduce the gating-based dual hyperloop convolution model, we see considerable improvement of the performance. When we add the momentum-driven twin network and comparative learning, we see further improvement of the performance. And the last stage is negative sampling strategy applied for the complete model. And we see that in this particular case, the performance is best. And the third test is to test the effect of hyperparameters on the accuracy. Here we have beta, one hyperparameter, and also we check the influence of value of beta, which changes from 0.1 to 0.9 with the step 1.9. And we check four chosen metrics for 2 data sets. And we see that when beta value is 0.5, the performance is best among all other possible values. So we chosen beta 0.5 for the best, most effective operation of the proposed method. Thank you for your attention.